Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker. Chapter 15, Part 1, Randomized Complete Block Design. All right. In a randomized complete block design, we want to control for some confounding variable. So rather than just randomize people into different treatments right away, what we do first is block based on some confounder, and then we randomize into treatments within each block. So we are going to examine the effect of T treatments in B blocks. So if we think of all of our subjects, first we think of a blocking variable. Let's just say the blocking variable in this case is age. So this is going to be under 18, 19 to 24, and 25 plus. From there, we're going to randomize into treatment 1 down to treatment T for each of these groups. And at the end of the day, we're going to examine some response variable. All right, so essentially the blocks are trying to make each of those groups more similar, so that you're not going to by chance have randomized people into treatments where it's like, oops, everyone who was very young, it just happened by random chance to be in this particular treatment. So what it does is it guarantees us more balance of the groups. So now for treatment 1, I will have a mixture of young under 18, 19 to 24, and 25 plus, and same with the rest of the treatments. So what are the main advantages of this design? We can compare T treatments in the presence of a single extraneous source of variability. The analysis is fairly straightforward and easy to construct. We can accommodate any number of treatments in any number of blocks. What are some of the disadvantages? Well, this is going to be easiest when we have a relatively few number of treatments. And essentially, when we're just trying to block for one extraneous variable, we have to assume that the effect of each treatment on the response, it should be the same from block to block. All right, so we have some new notation for the randomized complete block design, right? The blocks go from 1 to B, 1 up to B, right? The treatments still go from 1 up to T. Okay, so if we put the treatment in the rows and the blocks in the columns, then we can get Y11, that is the treatment 1, block 1, right? And YTB would be the person who got treatment T from block B. Okay, so our Y bar I dots, those are the sample means for the treatments, whereas the Y bar dot J's are the sample means for the blocks. Remember that Y bar, that's our overall sample mean. Okay, so how does this end up looking in terms of a linear model? All right, we have our Yij equals mu plus tau I plus beta j plus epsilon ij. Remember, the Yij is the response. It's the observation of the jth block receiving treatment I. Mu is the overall treatment mean, and that's an unknown constant. Tau I is the effect due to treatment I, also an unknown constant. beta j is the effect due to block J, an unknown constant, and epsilon ij is the random error associated with the response from the experimental unit in block J receiving treatment I. Remember that those epsilon ij's follow a normal distribution with mean 0 and variance sigma squared epsilon. The assumption of this model is that epsilon ij's are independent. And from that, we know that our yij's will follow a normal distribution with mu plus tau I plus beta j as the mean, and the variance should be sigma squared epsilon. So if we wanted to check this, we know that the expected value of yij should equal the expected value of mu plus tau I plus beta j plus epsilon ij. Well, since this is a linear combination, we can get the expected value of mu plus the expected value of tau I plus the expected value of beta j plus the expected value of epsilon ij. Now remember that mu, tau I, and beta j are unknown constants. So the expected value of mu should just be mu plus tau I plus beta j. And then the expected value of epsilon ij, well, this piece is equal to 0, right? So now we have that our expected value of yij should just be mu plus tau I plus beta j. That's what we found here. All right, our variance of yij should be equal to the variance of mu plus tau I plus beta j plus epsilon ij. All right, well, this is a linear combination, right? So we get the variance of mu plus the variance of tau I plus the variance of beta j plus the variance of epsilon ij, right? Well, essentially here, since the mu's, the tau i's, and the beta j's are unknown constants, this piece is just equal to 0. They don't vary. So the variance of yij is equal to the variance of epsilon ij, and that is just sigma squared epsilon, which is what we found here. Now, since epsilon follows a normal distribution, then y is also going to follow a normal distribution. So that's how we got that there was a normal distribution. So overall, the randomized complete block design, remember, essentially we're taking a variable that we're going to first split our subjects into, such as age, where we had young 18 to 24-year-olds and then 25 plus, right? And then we're going to randomize. So we're going to first create blocks and then we're going to randomize. All right. Some additional notation for the randomized complete block design is that we have our yij's, our y bar I dots, our y bar dot j's, and our y bar dot dots. But the thing that's new here is that we have the estimates of our parameters, right? So under the assumptions in the model, the summation of the tau i's and the summation of the beta j's should equal 0. So if I want to get the predicted y, right? If I want to get y hat ij, then that's going to be equal to mu hat plus tau I hat plus beta hat j, right? And by substitution, that's equal to y bar dot dot plus y bar I dot minus y bar dot dot plus y bar dot j minus y bar dot dot. And what I end up with is y bar I dot plus y bar dot j minus y bar dot dot. All right, so I hope you learned something today about randomized complete block design, and I'll see you guys next time.